Hello everyone, today I will be introducing a key concept used in road engineering known as the Road Safety Audit or RSA. In Malaysia, RSA is widely implemented by the Jabatan Kerja Raya or JKR to improve road safety at different stages of a road project. The main purpose of RSA is to ensure that roads are safe for all users including drivers, motorcyclists, pedestrians and cyclists. It helps engineers to detect possible design issues such as poor visibility, unsafe junction or missing road signs early in the planning or construction stage. When RSA is done, JKR usually applies RSA at different stages. For example, concept or feasibility stage, preliminary design stage, and existing road audit, usually for roads that are already in use. So auditors will usually check the road geometry, junction intersection safety, signage and road marking, lighting condition, pedestrian crossing, drainage and roadside hazard and traffic flow conflicts. So our group has conducted the RSA study at two different locations inside UiTM, which is first at the junction at Jalan Sarjana 1 near Law Faculty. Reasons for the selection area because the important connection point within UiTM campus road network. It also experienced regular traffic movement from student, staff and campus vehicles. Also allows observation of different vehicle movement, which is turning movement, merging movement, crossing movement. And lastly, visibility and road design concern. Next, we conducted a spot speed study as part of our traffic engineering field investigation. This study was carried out at Jalan Ilmu near College Melati UiTM, where the objective was to determine the actual travelling speed of vehicles under normal traffic condition. The purpose of this study is to better understand driver behaviour and evaluate whether the observed speeds are consistent with safe road design standard. Jalan Ilmu 1 experienced high interaction between vehicles and pedestrians. Many students cross the road from the engineering buildings toward College Melati parking area and nearby facilities. Suitable location to evaluate vehicles operating speed in a pedestrian active area. Also, it helps to identify potential speed-related safety risks. So, the apparatus that we used throughout this field investigation is firstly telecounter, radar gun, and also measuring wheel. Procedure for spot speed study. Firstly, the radar gun is switched on. Next, the trigger is pressed while capturing the vehicle that approaching to the operator. Then, the readings from the radar gun was taken and recorded. Then, the data is continued collected until we approach 50 data collection.
Firstly, moving to data analysis for spot speed study. Arithmetic mean speed by summing the products of our classmates' speeds with their frequencies, then dividing by our total sample size of 82, we found an average speed of 30.5 km per hour. Mode, most common speed range. Grouping the data showed that our modal class is 30 to 39 km per hour, featuring the highest concentration of 52 vehicles. For range, the total spread between our highest and lowest group speed is 40 km per hour. And variance standard and deviation. To understand how spread out the speeds are, we calculated a variance of 55. Taking the square root give us a standard deviation of 7.416 km per hour, which this indicates that most vehicle speeds divide by about 7.4 km per hour from our average. Standard error with a standard error of 0.7416 km per hour, we can confidently say our sample mean is highly accurate estimate of the true population mean. Finally, we can extract important operational speeds directly from our percentile graph. For P15 minimum disturbance speed found at 16 km per hour, this means 15% of vehicles travel slower than this, marking the lower boundary of normal traffic flow. For P15, the median speed, the exact midpoint of our traffic is 28 km per hour. Half of the drivers drove slower than this and half drove faster. And lastly, model speed from graph, the steepest part of our curve points to a localized modal speed peak of 56 km per hour within the curve trend.
Next, I will present the traffic volume analysis. Based on Table 1, a total of 513 vehicles were recorded during the 30-minute survey. Cars and taxi had the highest number with 259 vehicles, followed by motorcycle with 229 vehicles. While only 15 buses were recorded, no heavy vehicles such as lorry or big vans were observed. For the traffic direction, V1 recorded the highest traffic volume with 148 vehicles, while V2 had the lowest with 41 vehicles. Based on Table 3, cars and taxi made up 50.49% of the total traffic and contributed 518 PCU per hour. Motorcycle accounted for 44.64%, contributing 343.5 PCU per hour, while buses contribute 90 PCU per hour. Overall, the traffic volume was 1,006 vehicles per hour, or 951.5 PCU per hour. This shows that the traffic at the study area is mainly dominated by cars, taxi, and motorcycle with very few heavy vehicles.
The problem that we get by doing our experiment, the first one is uncontrolled pedestrian crossing. There is no clearly marked zebra crossing, pedestrian traffic light, or physical barrier guiding the pedestrian. People are crossing diagonally at traffic, forcing motorcycles and cars to slow down, which could cause an accident. Next, the vehicle is parked directly on the side of a narrow road. This forces oncoming traffic to squeeze past the vehicles while simultaneously dodging a large group of pedestrians crossing the street. The third one is vehicles tend to out of road alignment, especially heavy vehicles like bus and lorry, which endanger other vehicles from the opposite direction. Lastly, some vehicles were speeding at the curved road, increasing the percentage of the loss of traction, which is understeer or oversteer, which will lead to an accident. For the solution, we paint a high visibility zebra crossing pad with a pedestrian activated traffic signal, so the pedestrian can halt traffic safely when boarding. Next, we clear safety buffers and signage. Install a highly visible no parking and advance warning signs before the narrow stretch to prevent civilian vehicles from blocking the road. Then, we can put optical speed bars, paint transverse white lines across the lane that get progressively closer together as drivers approach the hazard. This creates the optical illusions that the vehicle is accelerating, naturally prompting drivers to slow down and maintain better lane control. And lastly, install our speed humps ahead of the curve to physically and audibly prompt drivers to slow down.